Welcome back. We have been discussing a lot about scalar couplings, coupling mechanism, varieties of splitting patterns, when different chemically equivalent, inequivalent groups are coupled, intensity pattern, and the nomenclature used for the splitting pattern like doublet of triplet, quartet of triplet, varieties of nomenclatures. Everything we have discussed at a stage, and we also talked about varieties of coupling strengths possible. Now, continuing further quickly, there is no point in continuing further. See, there is no end for it. We can keep on discussing on this scalar couplings itself for several hours. At some stage, we'll have to put a stop. I hope I have given you an idea about what is a scalar coupling, how we can get information, etc. But you will have to take it further by reading a lot of voluminous amount of literature is available, books are available, you can continue. But at the moment, today I'll give you a few information about strength of the coupling, little bit, varieties of coupling possible, cis, trans, geminal, etc. And I'm going to quickly end this, and then we move over to analysis of the spectrum and different spin nomenclature, etc. Okay. So first thing is, of course, look at the type of coupling we have. I already said we start with one bond, two bond, three bond coupling. I discussed three bond coupling if it is cis and trans. I also said trans coupling in many example like olefins and substituted ethylenes, etc. Trans coupling is larger than cis coupling. Geminal coupling also has some interesting things. For example, molecules like this, if I consider geminal coupling here, two bond coupling, it is minus 6 hertz. Whereas in this molecule, where C double bond O is attached, geminal coupling is 42.2 hertz. So you cannot simply say a scale is there where we can say because of this, this is the coupling. Unlike cis and trans vicinal coupling, where by and large we know trans coupling is larger than cis in many examples which I am going to tell you today. Geminal coupling can vary like this, and sometimes it can have a negative sign also. That is the important thing. You should see in this example, coupling starts from minus 6, goes up to 42.2 hertz in just mere change of the substitution. Look at this ring and look at this is only a small change here, and here C double bond and C double bond O. The coupling changed drastically. Now similarly CH2, CHX type of molecule if you consider. Now geminal coupling between these two protons if you consider, and if it is non-equivalent I'm talking, in which case what happens if I have a substitution X? Depending on that 2J coupling can be, depending upon what is X, it can be lithium, proton, Pr2, Cl, etc. It can vary from plus 7.1 to minus 3.2. Systematically it is changing, you can see that. The substitution has a tremendous effect on this geminal coupling, including the magnitude and also the sign. Okay. And this is N-alkanes. If you consider this type of molecule, this can undergo rotation like this, which can have orientation like this. It can have a phi angle of between this three proton and the other one, between the CC bond, there can be a rotation. And if the angle of rotation, if it is it is phi is equal to 60 degree, 3J coupling can be 2 to 5 hertz. If the phi angle between these two is 180 degrees, it is 10 to 16 hertz. Look at this one. How when the interchange is going on between this conformation. For this conformation, when phi is 180, coupling can be very large, of the order of 10 to 16 hertz. So it can give you information about the conformation, decoupling. You can use to get some information about alkanes. For example, if I take cyclohexane, I'm just giving you chain structure conformation. Coupling between two axial protons is larger than between equatorial and axial and with equatorial protons. In simply, I will tell you, if I have a three bond coupling between axial and axial protons, this is larger than axial equatorial coupling, which is approximately equal to equatorial proton. Remember this point. Take an example, this 1-2 coupling, J12. This can be 14.5 hertz with negative coupling, negative sign. Whereas J13, this between this and this can be 2.2 hertz. Between 1 and 4 here, this can be 10.6 hertz. So this coupling information can also give information, coupling, strength of coupling can give idea about type of conformations in cyclohexanes also. And if same is true even in cyclohexane derivatives also. Look at this molecule. If I take this one, the axial to equatorial coupling is about 2 to 4.5 hertz. Okay, now in this molecule on the other hand, it is 8 to 11 hertz. Most important, you see the 3-bond coupling for this structure, and this is cis and this is trans. 3-bond cis coupling is 4 hertz, trans is 9 hertz. This can give you information about the conformation of cyclohexane derivatives also. Cyclopropane as another thing. This is a classic example in which cis coupling is larger than trans coupling. See, when phi is trans is phi is approximately equal to 0 degree. It is a cis conformation when phi is approximately equal to 135 degree. If you now find out the J coupling, if the J is cis is quite large, then you know it is what is the angle of this. So very easily you can approximately get the from the coupling strength, whether the cis are strong or trans, you can get the angle. Another point is aromatic systems. You always come across aromatic systems in your molecules. Look at this one. This is orthocoupling. We should not write AB. That's wrong. AB means it is strongly coupled. It is only a label, not coupling number. It's spin system nomenclature. Orthocoupling can be very large, 6 to 10 hertz. Remember, in the case of substituted aromatic, I'm talking. It can be have some substitution here or here like that, no problem. Like benzene, where I showed you, orthocoupling varies from 6 to 8 hertz. Or similarly, meta 1 to 3 hertz, para 0.5 to 0 to let's say 1 hertz. Here also substituted aromatics also. Ortho, meta and para coupling, 3 bond, 4 bond, 5 bond varies of this order. Here it is, ortho is 6 to 10, meta is 1 to 3, and para is 0 to 1.5 hertz. So vicinal coupling, if you look at it, the vicinal coupling, especially 3J coupling, if you take, it depends strongly on the dihedral angle. Very strongly on the dihedral angle. Look at this one. When dihedral angle is 90 degree, this coupling is close to 0. When it is cis orientation, it is anywhere between 6 to 10 hertz. When it is trans orientation with 180 degree, the coupling can be quite large, can up to be at least starts from 8 to 12 hertz. So the 3-bond vicinal couplings gives an idea about axial orientation, axial equatorial, equatorial. Depending upon the angle theta, you have different coupling strengths. So you will get information about the conformation of the molecules. Another point is, these are some information I am giving you. I mean, just to get a feel for it. You don't have to worry about it. You don't have to even mug up and remember. It is just for the sake of giving it information so that you should know when you are analyzing the spectrum what are the points to look at. Okay, this information you can also get from the books. See, as the ring sign keeps on decreasing here from 8 members, 6 members, 7, 6, 5, 4, 3, except some anomaly here, steadily this coupling strength decreases as you go down. Same way here also, you see, 3J coupling, ortho coupling here, 5.7, 5.7, 3.1, 2.1, and as the size of the ring reduces, the coupling strength steadily decreases. So decreasing the angle, HCS bond angle, results in increase in 3JHH. This is an information, okay? Of course, it also depends upon the bond order. In this case, we remember in the chemical sheet when we were analyzing, I said all the 4 are equivalent. The ethylene proton comes at 5.29 ppm. I told that. I hope you all remember. The coupling in this case is 11.6. You understand? You ask the question, how I got the coupling here? All are equivalent. It will give a single peak. Similar to benzene, it gives a single peak. Okay. So the question is, how did we get the coupling? Is a point we'll have to discuss later. I will tell you how to get the coupling information in equivalent spin system. For example, hydrogen molecule, I told you, 1-bond coupling is 276 hertz. How do I get that? that information. In one of the classes, I will discuss how to get the coupling in equivalent systems where coupling is not reflected in the spectrum. So now similarly here, if you look at it, this is 7.6, whereas in this case, depending upon this, this is 6.0, this is 8.6. So like this, heterocyclics also have smaller coupling constant compared to hydrocarbons. These are all use of Karplus equation is something very important. This is a very famous Karplus equation. It's a quadratic equation of cos phi. Phi is the diagonal angle. It will give you a lot of information about the varieties of systems. This was first theoretically predicted by Karplus, where the A, B, and C are constants. Of course, now over the years, this Karplus equation has undergone lot of modifications, and the coupling values people have derived depending upon different types of system, different nuclei, etc. They have worried about 3-bond carbon proton coupling, 3-bond heteronuclear coupling, and varieties of information about Karplus curve is available. This is only a basic equation I am giving you. All you have to remember is the quadratic equation cosine of phi, okay, where phi is the diagonal angle. The most interesting information you can get from Karplus equation is in the olefinic system. If you know transcoupling, this information is, you should remember, transcoupling is larger than cis. In substituted ethanes, gauge coupling is less than trans, and similarly equatorial in this thing. Other case, cyclohexane we discussed. Now, the important application is Karplus equation will tell you. It can help you to distinguish between axial and equatorial protons, especially in some natural products, based on the coupling strength. It's a very important information. In this molecule, this is alpha D glucose, it's a beta D glucose. This has a cis orientation, this is a trans orientation. Or in other words, this has axial and equatorial coupling. These two protons, axial and equatorial coupling. This is axial coupling. In other words, axial coupling, I told you, is much larger, about 7.4 hertz. Very interesting, right? So that's why looking at the coupling strength between these two protons, you can say whether it's beta D glucose or alpha D glucose. Fantastic application of Karplus equations. Okay. It can also distinguish cis trans isomers in olefins. As I told you, trans coupling by rule, general rule, is larger than cis coupling. Look at this molecule. If these two protons are in cis configuration, coupling is of the order of 12.3 hertz. If it is in trans configuration, it is nearly 16 hertz. Very large. So based on the coupling strength, you can distinguish cis and trans isomers. That's very useful information. Okay. Now we knew about 1-bond coupling, 2-bond coupling, 3-bond couplings, etc. But in one of the classes, when I was showing you the salient features of the coupling, I also said the coupling strength decreases with increasing the number of bonds sequentially. Let us say for 1-bond coupling is quite large. We saw that in hydrogen molecule it is 276. 2-bond is smaller than that, and 3-bond is even smaller. As you keep going far and far away, 4-bond, 5-bond is much smaller. Coupling strength drastically reduces after 3 or 4 bonds. Most of the cases, 4-bond couplings are very rarely seen, very small value. But in some specific examples, especially when you have molecules which are linear like this, or molecule which has a zigzag shape like this, in which case very long range couplings have been observed. Very long range coupling. For example, in this molecule, this proton and this proton are separated by 1, 2, 3 and 4 bonds. 4-bond coupling of 9 hertz. It is really large. 4-bond coupling almost practically goes to 0 in some cases. And in this example, we could see 9 hertz. The long range coupling. You see in this molecule, again linear molecule, 5-bond coupling of 3 hertz is seen. That's also quite large here in this molecule. So in a zigzag type molecule, you see 5-bond coupling is seen, 4-bond coupling is seen. So it is not that there are no deviations from the general rule. The general rule is coupling strength decreases with increase in the number of bonds, but does not mean there are no deviations. In many examples, we have observed long range couplings of 4 bonds, 5 bonds, 7 bonds away, 8, 9 bonds away. I'll show you one example today. 2 protons separated by 9 bonds, coupling has been seen. These are all very interesting. Of course, these are rare examples, but what I'm trying to say is you have to be cautious while analyzing the spectrum. Don't generally be under the impression, okay, after 3 bonds, no coupling, it is practically 0, and this coupling is for a different reason. This peak is coming for a different reason. No, there are deviations. You have to be very careful. Take all these factors into account while analyzing the spectrum. Okay. So this is an example like this. In this type of molecule, 4-bond coupling is 1.2 hertz. Here you see 4-bond coupling of 18 hertz between this to the proton to this proton. Enormously large. That has been seen. And this is a classic example. In a linear chain like this, the coupling between this proton and this proton of the order of 0.4 hertz has been seen. Remember, this proton and this proton are separated by 9 bonds. 9 JHH has been seen. A very rare example, but it is possible. So, NMR, many cases, you cannot apply a general rule and as a dogma and say, yes, this is what it is. No. Many interesting things do happen, and you have to take all those things into account before analyzing. So far about the varieties of information I wanted to give on scalar couplings and coupling strengths, etc. Now, one more information. Remember, when I was giving the salient points, I also said J coupling is independent of the magnetic field. Unlike chemical shifts, where chemical shift is linearly dependent on the magnetic field, J coupling is independent of the magnetic field. Let us see this example. I have taken the spectrum of some hypothetical molecule. Of course, looking at the spectrum, by now you must be experts, you must be able to say, what is this molecule? Hypothetical molecule. This is a triplet, means it is attached to a CH2 group. And this is a quartet, means it is attached to a CH3 group. It means it is a molecule containing CH2 and CH3, some hypothetical molecule with other substitution. Now, this is a spectrum in 200 megahertz. I will measure this in frequency. In 200 megahertz, 1 ppm is 200 hertz. What is 3 ppm? 600 hertz. Now, if you measure the separation between adjacent peaks, you are going to get coupling constant. What is the separation? I measure it is 8 hertz. Okay, that is the 8 hertz coupling constant we measured. Let us do one more interesting thing. We will now go to higher frequency spectrometer. Same molecule will record the spectrum and 400 megahertz. What is going to happen now? Same 1 ppm we measure, 400 hertz. Remember, frequency to ppm to frequency conversion, we have done lot of examples. 1 ppm is 400 hertz. What is 3 ppm? 1200 hertz in 400 megahertz. Measure the J coupling. Fantastic. It's not changing. It is very interesting, right? The chemical shift change linearly with field, but J coupling is not changing at all. The separation between the peaks split because of J coupling do not get altered with the magnetic field. This is the information I wanted to give you. Remember, when you are measuring the couplings, irrespective of the magnetic field, irrespective of the spectrometer you record, that remains same. Okay. Next, we will analyze one spectrum. Instead of analysis, I will say we will generate a spectrum. We will build a spectrum using family tree approach. Let us take this. I give you a problem. I'll take one molecule which contains a CH proton. Read this question very carefully. I take a molecule which contains a CH proton and two CHs, M and R. And remember the coupling constant is 8 Hertz and 15 Hertz. Okay? What is the coupling constant? The coupling constant of these two CHs with respect to this. Okay, with respect to this CH, the coupling constant of CHs M and R is 8 Hertz and 5 Hertz. Interestingly, it is also coupled to CH2 with a coupling strength of 6 Hertz. Now, my question is, we have to generate a spectrum, theoretical spectrum, in a stick plot. We'll take a stick plot of this one. Now generate the spectrum. How do we do that? Simply adapt family tree approach. Take the CH proton A. Without any coupling, it has to be a singlet. Correct? It is a singlet. Now it is coupled to two CHs, M and R, with the coupling of 8 and 5 Hertz. You may also remember, I told you when you are analyzing the multiplicity pattern, order of coupling which you take does not matter. It is immaterial. Now you can take this coupling first and make it a doublet, or this first and make it a doublet. Doesn't matter. So both we can take. First we will take couple with M. It's 8 Hertz. You can take R also, no problem. I took M and the separation is 8 Hertz. So this CH proton, split this into a doublet. Now what about this proton R? That also will split each of the line into doublets. Now what happened? It was doublet, now it become doublet of doublet, DD. It is DD now. That is not the end. This proton is also coupled to CH2s. These protons, that means each line of this doublet of doublet, what will happen when it splits with CH2? Remember, magnetically equivalent spins, you have to use 2Ni plus 1 rule. What is going to happen now? Each line of this doublet of doublet splits into a triplet. So, what do you call this pattern? This is doublet of doublets of triplets. So, this is how we can generate the multiplicity pattern. You understand how easily we can do? This is we generated theoretically, assuming a hypothetical molecule. But in real spectrum, you have to go backwards. You will be given only this multiplicity pattern. Start analyzing and finally arrive at the chemical shift and all these coupling values. That is your job. That is what finally analysis has way you have to do for analysis. Alright. So I think I have given a lot of information about scalar coupling, and now we also took an example how to generate the multiplicity pattern theoretically as an example. Now we will go to analysis of spin systems using Pople notation and the spectrum. That is the next step. So I will stop this and then we will go into the next one, which is called Pople nomenclature. I'll continue this in this class today because this is very important. Most of you will come across this analysis part. I don't know whether you people have heard of peak coupling, strong coupling. I did mention it. And if you really get deeper and deeper into NMR analysis, if you become a hardcore NMR spectroscopy, you must know all this Pople nomenclature, analysis of the spectrum of different spin system, etc. We will start with what it is now. First, this if you have to do the spectral analysis using Open notation. First thing you should know is whether what is the spin system, whether it is strongly coupled or weakly coupled. That's a very important aspect you should remember. Unless you know whether it is strongly coupled or weakly coupled, you cannot analyze the spectrum so easily. This is weakly coupled, this is strongly coupled. Now the question is, what is weakly coupled spin system and what is strongly coupled? I have already told you in one of the classes what is a spin system, what is a strongly coupled spin, so what are strongly coupled spins, what are weakly coupled spins. I gave a quick description about those things. I hope you remember. Otherwise, now you see the understanding of what is that one. I'll take the example of what is a weakly coupled. Remember, weakly coupled spin system is the one where this chemical shift separation must be much larger than the J coupling. I consider two spins. Let us say one proton is here with a coupling this, other is here with a coupling like this. What is the chemical shift separation between this and this? This is, let us say, delta. I'll measure this as delta. This separation are called delta, no problem. If this value is sufficiently larger than this is J coupling. Okay, this is sufficiently larger than this J coupling, then you call it a weakly coupled spin system. How much should be the larger is the next question. If this is 10 hertz, if this is 11 hertz, is it okay? No. There is some empirical rule. There is no hard and fast rule, but some empirical rule. It is the ratio of the chemical shift separation between the spins and to its coupling constant should be very much greater than 1, and that should be at least greater than 50 times. You understand? Now let us take a simple example. I have two protons coupled, giving rise to doublets each. The chemical shift separation between this and this, let us say, is 500 hertz. The J coupling between these two is only 10 hertz. Now what is my R? 500 divided by 10. It is 50. So it is the weakly coupled spin system. On the other hand, I will take this chemical shift separation is only 20 hertz. My coupling is also 20 hertz or 10 hertz. What happens? 20 by 10 is only 2. So it has to be sufficiently larger. Since the ratio is not very large, you call that spin system as strongly coupled. Remember, a weakly coupled situation is one where this chemical shift separation divided by its coupling constant should be at least 50 times, more than 50. Some books write in a different manner. Okay, you understand? Some books write inverse of this. They write J over delta delta. In which case, take the inverse of this. In which case, if this formula is used, then this has to be very much smaller than 1, like of the order of 0.02. In some books follow this, some books follow this. Don't have to worry about it. But just remember one thing. Conceptually, the chemical shift separation should be sufficiently larger than coupling constant. Then the spin systems are weakly coupled. Is it clear for you? Now, we'll see what are homonuclear weakly coupled spin system and heteronuclear weakly coupled spin system. Okay. Consider a molecule like this. This proton and this proton, the chemical shift separation is 3.75 ppm. You know, when it is expressed in ppm, you know how to convert to frequency. Let us say I am recording the spectrum at 500 megahertz. For purpose of calculation, let us make it 4. Easy to multiply. 4 into 500 is 2000 hertz. What is J coupling? 2.9. 2000 by 3, let us take it 3. 2000 by 3, close to 600. That means the very weakly coupled spin system. Understand? Now take another example. between this proton and this proton. Chemical shift separation is 0.98. Take 1 ppm. In 500 megahertz, 1 ppm is 500 hertz. What is the coupling? 5.6. Now 500, you have to take it divided by 5.6. What is this? Close to 100. That means this is also weakly coupled spin system. So very easily you can understand what is strongly coupled and what is weakly coupled. And this can happen, weakly coupling, only in 100 megahertz. Remember, the chemical shift separation depends strongly on the magnetic field. One important point I want to tell you, if your nuclear spins coupled are very strongly coupled, that means chemical shift separation is not much large compared to J coupling. Let us say you are recording the spectrum at 100 megahertz. What you will do to make it weakly coupled? You have to go to very high magnetic field. Let us say in 100 megahertz, if it is strongly coupled, I'll go to 800 megahertz. Chemical shift becomes very large. Then it becomes weakly coupled. So the field has a tremendous influence on converting strongly coupled to weakly coupled or vice versa. Okay, this is the important point you must remember. In the case of heteronuclear, another interesting thing, take this molecule, proton and fluorine. The question is, are they homonuclear, are they strongly coupled or weakly coupled? I don't have to tell you. You will be in a position to answer yourself now. Because remember, proton and fluorine are large separation in the resonating frequency. In proton, in 500 megahertz comes at 500, whereas fluorine comes somewhere around 470. 30 megahertz difference is there. Huge separation. You can call it as chemical shift separation of the order of 30 megahertz. What is this coupling? Only 10 hertz or 15 hertz. This means heteronuclear systems are invariably weakly coupled. Please remember, when I give the example for heteronuclear spin system and I ask you whether it is strongly coupled or weakly coupled, immediately it should come to your mind, this such type of heteronuclear systems cannot be strongly coupled. They always have to be weakly coupled. This is a very important point. Heteronuclear case can never be strongly coupled. So now I will give you an example of hormone heteronuclear weakly coupled spin systems in labeled molecules. Take an example like this. I will take this carbon and this carbon, both I label. Label means chemistry I will do in chemically synthesis. Somehow I make it 100% abundant instead of 1%. When you say 100% abundant, it's like proton or fluorine. Then you can see the coupling between these two. That happens when they observe the coupling, it is about 67 hertz. But chemical shift separation is 141 ppm. It is quite large. So let us take 600 megahertz. 600, okay, easy to calculate. I will take 800 megahertz. What is carbon chemical carbon resonating frequency? We have been discussing for so many times. 4 times less gamma. So 200 megahertz. That's why I took that example. Now what is 1 ppm of carbon in 800 megahertz? 200 hertz. 200 into 141 ppm. Very large. Whereas coupling is 67 hertz. This is at homonuclear labeled systems, they can also be weakly coupled. Take for example this molecule. Nitrogen 15 is there and carbon 13, both are labeled. And this coupling is only 14 hertz. Now the question is it strongly coupled or weakly coupled? I don't have to tell you. You know the answer. Because they are far away separated in the resonating frequency. If in the 300 megahertz, carbon comes at 75, nitrogen comes at 30 megahertz or 20 megahertz, whatever it is. It is 10 times lower gamma. Okay, 30 megahertz. Now what is the difference? Where is 75, where is 30? Such a large chemical shift separation and coupling is only 14 hertz. That shows heteronuclear system like this, it's always weakly coupled. You get the point now. I hope you understood everything. So now I'll stop here for the day. In the next class, I will bring in this strong coupled spin system. So far, we're discussing about weakly coupled. Then we'll look at the spectrum of strongly coupled and weakly coupled 2 spin, 3 spin, 4 spin, etc. How to analyze and how to give the nomenclature for this using Popper. So that we will continue in the next class.